Hello everyone, welcome to the lecture series on VLSI design. Myself Professor Meenaxi T, Department of ECE, KLS VTIT, Halia. In the previous lecture we discussed IV characteristics of a MOSFET. In this lecture we are going to cover CMOS inverter, DC transfer characteristics, beta ratio effects and noise margin. DC transfer characteristics of a circuit relate the output voltage to the input voltage, assuming the input changes slowly enough that the capacitances have plenty of time to charge and discharge. So this figure represents a CMOS inverter circuit. So it consists of a PMOS device and an NMOS device. Both gates shorted, supplied with input variable, both drain shorted, and gives you the output of a inverter. PMOS topmost end is connected to VDD, NMOS lower end is connected to ground. Let us assume VTN as the threshold voltage for N channel device and VTP as the threshold voltage for P channel device. VTN is always positive whereas VTP is negative. So let us compute VGSN now. VGS for NMOS device can be written as VG for NMOS minus VS for NMOS. Gate voltage for NMOS is Vin, source voltage for NMOS is 0, therefore VGSN is Vin. VDSN is drain voltage for NMOS minus source voltage for NMOS. So drain voltage is Vout, source voltage is 0, so VDSN is Vout. VGSP is gate voltage of PMOS minus source voltage of PMOS. Gate voltage of PMOS is Vin, source voltage of PMOS is VDD. Therefore, VGSP is Vin minus VDD. VDSP is Vout minus VDD. So, this characteristic in first quadrant is IV characteristics for NMOS device. So, VDSN versus IDSN for different values of VGSN. And the curve in the third quadrant is for PMOS device, VDSP versus IDSP. PMOS threshold voltage is always negative, so the characteristics lies in the third quadrant. As you increase VDS initially, current increases. Once channel gets pinched off, the current remains constant. That is, IDS is independent of VDS. Same applies for PMOS device. To obtain DC characteristics, let us overlap NMOS characteristics and PMOS characteristics. So PMOS characteristics was in third quadrant. If overlapped on N, the P characteristics is shifted to first quadrant. So both N and P characteristics are overlapped to obtain DC characteristics of a CMOS inverter. So if we overlap the characteristics of NMOS and PMOS, this is the curve we obtain in first quadrant. For NMOS, Vin is exactly equal to VGSN. So if Vin is 1.5, VGSN will be 1.5. If Vin is 2, VGSN will be 2. If Vin is 2.5, VGSN will be 2.5. If Vin is 3, VGSN is 3. If Vin is 3.5, VGSN is 3.5. So this black color characteristics is curve for NMOS, VDS versus IDS for different values of VGS. So VGS is exactly equal to input for NMOS. For PMOS, VGS is Vin minus VDD. If my input is 1.5, VGS for PMOS is 1.5 minus VDD, that is 5. So VGSN will be 3.5. Similarly, if my input is 2, VGS for PMOS is 2 minus VDD, that is 2 minus 5, that is 3, neglecting the negative sign. If my input is 2.5, VGSP for PMOS is input voltage 2.5 minus VDD, so VGSP is 2.5. Similarly, if my input voltage is 3, VGSP is 2. If my input is 3.5, VGSP is 1.5. So region A can be considered as input voltage 0 or input voltage less than threshold value. So when input is 0, PMOS device will be in on state. When input is 0, NMOS is in off, so we say NMOS operates in cutoff region, and when input is 0, output will be VDD. So coming to region E is when Vin is 5 volt. Suppose this is and Vin is 0. If input is 5 volt, NMOS transistor will be in on state, hence we say N operates in linear region. PMOS will be in off state, and we say PMOS operates in cutoff region. And if input is 5 volt in region E, it means output will be 0. Coming to region B, when the input is 1.5. Region C is when the input is 2.5, and region D somewhere around 3.5. So region B, when the input is 1.5. So 1.5, this characteristics is for NMOS, and this blue 1.5 is for PMOS. So both N and P intersect at this point. So if you observe N and P characteristics at this intersection point, N has a straight line, whereas P has a linearly increasing curve. So it means P operates in linear region, and since N has a flat line, so this region of operation will be saturation. So if you remember the characteristics of N or P, initially current increases for applied VDS, that is termed as linear region. Later the current remains constant, and this is termed as saturation region. So if the intersection point is a flat line, then we term it as saturation. If it has a linearly increasing curve, it is linear region. If you consider 2.5, this is the intersection point of both N and P. Hence region C, both NMOS and PMOS operate in saturation region, and Vout is exactly equal to 2.5 in region C, and input is 2.5. Region D is when input is 3.5. This is the characteristics for NMOS for 3.5, and for 3.5 this is the curve for P. So both P and N overlap at this point. So PMOS has a flat line, so for 3.5 PMOS operates in saturation region, whereas NMOS 3.5 it has a linear curve, so NMOS operates in linear region. So when input is 0, PMOS turns on, hence output is VDD. When input exceeds threshold value, NMOS device operates in saturation region, PMOS operates in linear, and output is less than VDD. At region C, both transistors operate in saturation. The input and output voltage at region C is exactly VDD by 2. Hence region C is termed as midpoint or switching point. In region D, that is somewhere around 3.5 input value. P operates in linear region, P operates in saturation region, and NMOS operates in linear region, and the output is less than VDD by 2. Region is when input is exactly 5 volt. When input is 5 volt, NMOS is in on state, that is NMOS operates in linear region, PMOS is off, that is cutoff region, and the output is exactly 0. So this crossover point where Vin equals to Vout is called inverter threshold voltage. So now let us write the operating region equations for NMOS and PMOS. NMOS operates in cutoff region if VGS is less than VT. VGS for NMOS is Vin, so Vin less than VTN. NMOS operates in linear if VGS is greater than VT and VDS is less than VGS minus VT. VGS for NMOS is Vin, so once you substitute you get Vin greater than VTN. VDSN is Vout, therefore Vout is less than Vin minus VTN. In saturation region, the condition for NMOS is VGS is greater than VT and VGS for NMOS is Vin, so Vin greater than VT. VDS is greater than VGS minus VT. VDS is Vout, therefore Vout greater than Vin minus VTN. For PMOS, it is exactly dual of NMOS. For NMOS, VGS is less than VT. For PMOS, it is greater than threshold. VGS is Vin minus VDD greater than VTP. So VDD from left hand side is shifted to right hand side. Therefore, we will obtain Vin greater than VTP plus VDD. PMOS to operate in linear region, the conditions are VGSP greater than VTP. Once you substitute VGSP and simplify, you get Vin less than VTP plus VDD. And PMOS to operate in linear region, VDSP is greater than VGSP minus VTP. So substituting VDSP and VGSP, VGSP is Vin minus VDD, VDSP is Vout minus VDD. So substitute and simplify, you will get Vout greater than Vin minus VTP. Similarly, for PMOS to operate in saturation, the conditions are VGSP less than VTP, that is Vin less than VTP plus VDD, and VDSP less than VGSP minus VTP, that is Vout less than Vin minus VTP. So region C, both the transistors operate in saturation region, therefore same current flows through N and P device, hence we can equate both the current terms. IDSP equals to minus IDSN. Expression of current in saturation region is given by beta by 2 VGS minus VT square. IDSN, current for NMOS device. Beta by 2 VGS N minus VTN square. VGSN is Vin, therefore IDSN is beta by 2 Vin minus VTN square. IDSP, P also operates in saturation region, so the expression of current is beta by 2 VGSP minus VTP square. Substituting VGSP, that is Vin minus VDD. IDSP will be beta by 2 Vin minus VDD minus VTP square. So IDSP is equal to minus IDSN. So both denominator 2 will get cancelled. Beta P is shifted on right hand side, therefore we will be getting this expression. Cross multiplying the terms, we'll be getting Vin minus VDD minus VTP equals to minus Vn square root of beta n by beta p plus Vtn square root of beta n by beta p. Once you simplify, you'll be getting Vin equals to VDD plus VTP plus Vtn square root of beta n by beta p divided by 1 plus square root of beta n beta p. So assuming Vtn equals to minus Vtp and beta n equals to beta p, we'll have Vin equals to VDD by 2, that is 2.5. So this is a crossover point where Vin equals to Vout equals to VDD by 2 is known as input threshold. So for a CMOS inverter, if Vtn equals to minus VTP and beta n equals to beta p, the threshold voltage is VDD by 2, exactly 2.5. If the inverter beta ratios are different, then they are known as skewed inverter. If beta p by beta n is greater than 1, the inverter is known as high skewed. So a high skew inverter has a stronger PMOS transistor and the switching point is greater than VDD by 2. If beta p equals to beta n, switching point is exactly 2.5. If beta p by beta n is greater than 1, PMOS is stronger and switching point is greater than VDD by 2. If beta p by beta n is less than 1, the inverter is low skewed. Low skewed inverter has stronger NMOS or a weaker PMOS and the switching point is less than VD by 2. If beta p by beta n equals to 1, the inverter has normal skew or is unskewed. As beta ratio changes, the switching threshold moves. If beta p by beta n is equal to 1, then the switching point is 2.5. If beta p by beta n is greater than 1, the curve shifts towards right side, and if beta p by beta n is less than 1, the transfer characteristic shifts towards left side. Next concept is noise margin. Noise margin is closely related to DC voltage characteristics. Noise margin determines the allowable noise voltage on the input of gate terminal so that the output will not be corrupted. There are two parameters in noise margin: low noise margin, high noise margin. Low noise margin is difference between maximum low input voltage and maximum low output voltage. High noise margin is the minimum high output voltage and minimum high input voltage. If the inputs between VIL and VIH are said to be in intermediate region or forbidden zone, they do not represent any legal digital values. Therefore, it is required to have VIH as close as possible to VIL. If low noise margin or high noise margin for a gate are too small, the gate may be disturbed by the noise that occurs on the input. An unskewed gate has equal noise margin, which maximizes immunity to arbitrary noise sources. If the gate sees more noise in the high or low input state, the gate can be skewed to improve that noise margin at the expense of other. If both the threshold voltages are equal, the noise margin increases as threshold voltages increases. So gain at these points is -1.